Hi there! You were taught probability wrong. Well, you were probably taught probability wrong. I have an easy way to check. Just one question. This candy comes in 4 colors. Red, green, blue, white. I ate 10. 4 blue, 3 green, 2 red, and 1 white. What's the probability the next one is blue? The correct answer is C.
Is that the right answer? I'm right. How come? Ugh, wrong again. Unfair.
The 6 answers were calculated using 6 slightly different methods of probability. Theoretical probability got A, experimental probability calculated D, and Bayesian probability calculated the others. The Bayesian probability was done with a Haldane's prior, a Jeffreys prior, or a Laplace's prior on either a beta distribution or a Dirichlet distribution. The rest of this video only has a difficulty level of primary school, and it's mostly focused on why the answers A and D are wrong, which is weird, and then how to actually calculate all 6 of those answers, which is easy and at a primary school difficulty level. The next video has a difficulty level of calculus and focuses on why C is the correct answer while the other answers aren't. I need a new candy example to explain this. I'll fill the bag with 10 million yellow candies and 10 purple candies. Now introducing Sunrise Paradox Candy, 2 flavors, yellow and purple. The yellow candy gives you +1 experience points, and the purple candy causes instant death. Now kids, and any other idiots that need it explained to you, never eat from a box labeled with poison. That's just common sense. Let's play which flavor is next and welcome our first loser, Mr. Theoretical Probability. Would you eat the next candy?
No, are you crazy? It's labeled poison.
Well, what do you think is the probability a poison comes out next?
There's 2 choices, so a half.
I'll make a bet with you, repeatedly, just by looking at the candies. If a purple comes out, I'll pay you 100. But if a yellow comes out, you pay me 2.
Wow, on average I will win a half times 100 minus a half times 2 equals 50 minus 1 equals 49 each round.
So, 10 yellow candies came out. You owe me 20.
Well, that's just bad luck. Let's keep going. I'm sure to win soon enough.
Okay, let's do 600. As I expected, they're all yellow again.
Wow! That's astronomically bad luck. Like nowhere in the lifetime of the entire universe should anything so rare even exist.
Unless the probability isn't a half. Would you like to recalculate?
No, that would mean learning from experimental data. As Mr. Theoretical Probability, I can't.
That's stupid. Go away. He wasn't smart. Let's play which flavor is next and welcome our second loser, Mr. Experimental Probability. Mr. E, you don't just look at the label, right?
I don't use the label at all.
Then how do you calculate probability?
I only look at experimental data.
You mean what comes out of the bag?
Correct. Only that.
But you're a new contestant. You haven't seen any data yet. What will you do?
So I count 0 yellow candies and 0 total. Then I divide them. 0 divided by 0 equals... Divide by 0, error. Boom!
Wow, what impressive animation.
I'm back. Hey, not cool. I need some data to work.
Yeah, okay. I'll pull out just one yellow candy. Now what's the probability?
Oh, 1 yellow candy and 1 total. Divide to get 1 divided by 1 equals 1. Guaranteed.
Would you eat a whole bag? You're not afraid to die again?
By the rules of experimental probability, I'm sure there's no poison.
It's labeled poison.
I'm back. Okay. Smart people say I need more data to be accurate.
How much?
They disagree. Some say 20, others say 30. Let's do 99 to be safe. I already died twice.
Okay, 99. All yellow. Now what?
99 divided by 99. Guaranteed! Yum, yum, yum. Yeah! I'm back. Okay, more data. If it only takes 1 second per try, I can get 1,000,000 samples in 11.574074074074 days if I don't sleep.
Good thing they're free. I know the real probability. Even if you take 1,000,000 samples, the most likely outcome is all yellows.
Wow.
Yeah.
How much data is enough?
That's the wrong question.
Huh?
The question behind the sunrise paradox is, how do you calculate probabilities if all of your observations or experiments are the same? Paradoxes drive new math. The sunrise paradox shows that both theoretical and experimental probabilities have problems with them. It was found in 1763 by Richard Price. Bayesian probability solves this paradox, and it's not much harder to calculate. So, the original question, theoretical probability, only counts the label, not the trials. Experimental probability only counts the trials, not the label. Bayesian probability uses both. So the original question had 4 colors on the label, and it actually ran a trial 10 times to get experimental data. For the theoretical probability, you count 1 time for each one of the options on the label, and you're going to get a probability, the next one is blue, of 1/4. Experimental probability is going to count the trials. 4 blue came out of 10 trials total, so the experimental probability for a blue being next is 4/10. Bayesian probability uses both. For each of the colors, you're going to have a theoretical count and an experimental count. Let's count them up. But first, there's one small issue. Are you going to count 2 types, blue and not blue, or 4 types, the colors on the label? The question made it clear that there are 4 distinct types of candies, not just 2. It matters. There's 3 different kinds of not blue. Laplace's way to calculate Bayesian probability will give a theoretical count of 1 for each credible option before looking at the experimental data. When there's only 2 options, the probability of a blue is 5/12. When looking at 4 distinct options, the probability of a blue coming next will be 5/14. Haldane's way is just experimental. At the beginning, it gives a theoretical count of 0 for every credible option. It's worse than Laplace's method, and we've already gone through why. Jeffrey's way to calculate Bayesian probability gives a theoretical count of 1/2 for every credible option before counting the experimental data. When there's only 2 options considered, the probability of blue being next is 4.5 out of 11, or 9/22. When there's 4 credible options considered, the total theoretical count is going to go up to 2, and the probability of a blue being next is 4.5 out of 12, or 3/8. And this is how we get the correct probability for the next candy being blue. That's it. Does Bayesian probability really beat the sunrise paradox? Let's do the sunrise candy again with Bayesian probability. First of all, for the sunrise paradox candy, there are only 2 choices, yellow and purple. When we have an unopened bag, we're going to give a theoretical count of 1/2 to each one of them, and a total count of just 1. So the probability of yellow and purple is the same. They're both 1/2. It agrees with theoretical probability when there's no experimental data. When we pulled out just 1 candy, all we have to do is add 1 to the experimental count on the yellow side and update our probability for a yellow coming out. The total count for yellow is 1.5. The total count is 2. So the probability of a yellow being next is 3/4 now. After we pulled out 99 yellow candies, we need to update the experimental count for yellow to 99, giving us a total of 100, and a probability that a yellow comes out next is 99.5%. When we have 1,000,000 yellow candies coming out, the probability a yellow comes out next is 1,000,000.5 over 1,000,001. It's really, really close to guaranteed, but it's not 100% guaranteed. Okay, bye.